Now let's implement a packed struct that efficiently represents GPIO registers. We define a GPIO register struct where various GPIO pins are represented as Boolean values packed into a single byte alongside reserved bits for alignment. This compact structure allows for streamlined memory usage while enabling direct manipulation of individual GPIO pins. Next, we will explore a function called write-to-GPIO, which demonstrates the proper way to update the GPIO register state. Instead of modifying the GPIO registers directly using field access, which could lead to inconsistencies due to potential race conditions, we create a new GPIO register instance named newStates. This instance holds the intended GPIO state, and we then write this entire state to the volatile pointer representing the register. This encapsulation protects the integrity of the data by ensuring all changes occur simultaneously, preventing partial updates that could destabilize the system. By adhering to these practices, we gain not only performance efficiency but also reliability within our system's interactions with hardware components, key elements in systems programming. Now let's take a look at the packed struct we have defined named bitField. This structure showcases an efficient way to allocate bits in memory, allowing multiple fields to share the same memory locations. In this example, we have three fields, A, B, and C, each declared with varying bit widths. Particularly, A and B each occupy 3 bits while C occupies 2 bits. The compact nature of packed structs allows us to conserve memory, but it also requires careful handling of each field's offset. Next, we will see how the initialization of these fields works. We create an instance of bitField named bitField, assigning values to each of these fields. The real intrigue comes in the test case named packed struct addresses, where we can explore the memory addresses of these fields directly. By using pointers to access their addresses, we can verify that A, B, and C overlap in memory, demonstrating the essence of packed memory representations. This overlapping is double-edged. Although it saves space, it necessitates a deep understanding of how the fields interact to avoid unexpected behavior. Understanding these nuances equips you with the knowledge to effectively utilize packed structs in real-world applications. Now let's see how we can implement dynamic memory allocation for structs in Zig. In this example, we utilize the page allocator provided by Zig's standard library to create an instance of a custom struct, myStruct. This allocator serves as a means to manage memory explicitly, which is crucial in systems programming where performance and memory efficiency are paramount. We begin by defining the allocator variable, linking it to the page allocator. This enables us to use dynamic memory management capabilities that Zig offers. The create method is called on the allocator to instantiate myStruct. If this operation fails, it will invoke the catch unreachable clause, terminating the program, which underscores the importance of error handling in memory management. Once the struct is created, we use the defer statement to ensure the memory allocated for myStruct is deallocated automatically when the function exits, even if it exits unexpectedly. This practice not only prevents memory leaks but also promotes safer programming habits. After allocation, we can initialize and utilize myStruct by assigning values to its fields, showcasing effective dynamic memory usage while adhering to Zig's principles of manual memory management. Now let's take a look at how we can manage struct alignment in Zig to enhance performance. In the example, we define a structure named myAlignedStruct that contains two fields, A and B, each with explicit alignment specifications. The field A is aligned to 4 bytes while field B is aligned to 64 bytes. This careful placement not only ensures that the data is accessed more efficiently by the CPU, but also helps avoid potential performance penalties that can result from misaligned data access. Next, we create an instance of myAlignedStruct, initializing its fields with specific values. To test our alignment setup, we run assertions that verify the alignment characteristics of the structure and its fields. We check that myAlignedStruct itself has an overall alignment of 64 bytes, reflecting the alignment of its highest aligned field. Additionally, we verify that the types of the individual fields, A and B, conform to their specified alignments. This code demonstrates how Zig allows developers to explicitly manage data alignment, which is crucial for optimizing performance in systems programming. Now let's delve into error handling within structs. In the following example, we introduce a config struct that includes a field named value of type U32. The key feature here is the setValue function, which allows for modifying the value while enforcing a validation rule. The new value must not exceed 100. This function returns an error if the input violates this condition, demonstrating Zig's robust error handling capabilities that help maintain data integrity. As we implement the setValue method, we use a conditional check to determine if the new value is valid. If it surpasses the specified limit, we return an invalid value, allowing the function to signal an error back to the caller without compromising the state of the config struct. This approach exemplifies Zig's emphasis on safety, giving developers control over the state of their data structures. In the test function, we instantiate a config instance and then attempt to set its value to 101, which triggers the error handling mechanism. This reinforces the importance of data validation in system programming, ensuring that your configurations remain within acceptable bounds and preventing potential issues down the line. Now let's see how we can implement a method to compute values using structs in Zig, particularly focusing on the concept of destructuring. The function computeValues is defined to return a struct that contains two fields, min and max, both of type i32. This structure simplifies the handling of multiple return values by allowing us to package the related data together, for instance, returning both the minimum and maximum values from a computation. Next, we have a test case that demonstrates how to utilize the computeValues function. Within this test, we call computeValues and use the try keyword, which conveniently handles the error if the function returns 1. Once we have the result, we destructure the returned struct into variables min and max, which simplifies our access to these values. Instead of referencing the fields with a cumbersome syntax, destructuring allows us to unpack the content directly and improves code readability. Finally, we verify that the values of min and max are as expected, ensuring both the functionality and the utility of our approach in maintaining clear and maintainable code. Now, as we begin wrapping up this comprehensive look into advanced struct and memory management, I want to emphasize that while Zig provides powerful tools for struct manipulation and memory control, the onus is on you as the developer to use these tools judiciously. Proper understanding of bit manipulation, memory alignment, error handling, and dynamic allocation is the backbone of writing efficient and safe systems programs. Being mindful of these practices will not only make you a better Zig programmer, but will also equip you with the skills needed to build robust applications that can handle the complexities of real-world systems programming without compromising performance. In our next lesson, we will transition our focus onto concurrency and task management, essential components that can unlock the full potential of your applications, helping them operate efficiently in multi-threaded environments. Keep honing your skills and get ready for the exciting challenges that lie ahead.